Okay, so we're just learning to draw shear force and bending moment diagrams. So let's start off with some pretty simple ones. So in each of these cases, I want to draw the shear force and bending moment diagram. So I have a cantilever beam here with a load P at the end. This is kind of a classic problem. What I'm going to do, just to save some time, is I'm going to just tell you what the shear force and bending moments are at the end. I think you could probably figure it out. For example, if you sum forces, you will find that you have a positive force of P reacting up. And that, what kind of shear force is that? That's positive. And you will find that the resulting bending moment is equal to PL. What kind of bending moment is that? Positive or negative? Negative. So if you're working this at home or on the exam, I would expect you to go ahead and sum moments and forces and find those. But for these simple problems, I can just kind of cut right to it. So now to draw the shear diagram, if you remember, the first thing we want to do is look at the change in shear as the area under the load diagram. So looking at what I have, I've got a positive shear of what value? P. Right? I know that's where I'm starting. What should the change in shear be? The area under the load curve. What is the load curve throughout this structure right here? It is 0. So if I have a change of 0, that means when I get all the way to the end, I still have a value of P. And what's the shape of the curve here? Well, we know that the slope of the shear diagram is given by the value of the load at every point. And everywhere you look on here, except right at the end, the load is 0. And of course, 0 load means the slope is 0, and a curve with 0 slope looks like that. So I know that the shear is constant and equal to P. Now you may be thinking to yourself, well, man, did we just ignore that out there at the end? Actually, we didn't. In fact, if you look at a little chunk of the beam right here at the end, in this case, I'll draw it. Maybe a little dx chunk. Now the load P is applied right on the end. And of course, positive shear is up on that left face. And if you look at the equilibrium of this chunk, what's the shear internally? It's equal to P. And it's positive. And what's our diagram say it is? P and positive. So it's working. Just wanted to let you see that. Sometimes people get confused at what's happening out here on the end. I wanted to show you that. Okay, so now that I've got my shear diagram, I feel pretty good about that. Let's draw the moment diagram. To do that, I know that the change in moment is the area under the shear diagram. All right, do I know the moment at my starting point? I do. It's PL, and we've already said that that's what kind of bending moment? Negative. So I'm going to start at negative PL. The change in moment over the length L should be the area under the shear diagram. What is the area of the shear diagram? Well, it's just a rectangle. That's pretty easy. It's base L times height P, so it's positive PL. What's negative PL plus PL? 0. And if you look out here on the end, it's a free end. There's no applied moment, so it's 0. We also know that the slope of the moment diagram, the derivative, is equal to the shear. So let's go back and look at the shear everywhere. And what is it? Well, it's constant, it's positive, and it's equal to P. So a constant positive slope. And if you did look at it, you would see that that is a slope. I don't know why I wrote R, of P. Any questions about that one? So where's the maximum moment in a cantilever beam? Usually, under this kind of loading, it's at the connection. Where's the maximum shear? Well, it's everywhere, and it's the same. All right, let's go back over here and work this guy now. It's a little bit different. It's the same geometry, but I have an applied moment. So if I sum forces in the x direction, what's the shear at the support? 0. If I sum moments, I get a reactive moment in this value that is same value, m naught. So what's the shear at A? 0. The change in shear is equal to the area in the load curve. What's the area in the load curve? 0. So I should have 0 slope here. The slope of my shear diagram should be equal to the load. The load is 0. So this beam has no shear at all. 0 shear. Shear equal 0. What about moment? What kind of bending moment is this? Positive or negative?
Positive.
Positive. So I'm going to start at m naught. What kind of bending moment is that? Also positive. So I better end at m naught. Well, the change in moment between these 2 points is the area of the load shear diagram. What's the area of the shear diagram? 0. So it works. M naught plus 0 is m naught. That's great. What's the shape of the line look like here? Well, the slope of that line is equal to the shear. And what's the shear? 0. So a curve with 0 slope in our system is horizontal, and you end up with a system that has constant moment everywhere. So these are baby problems, kind of first step problems, right? Would you get something like this on the exam? Oh, guaranteed no. Guaranteed. But I want you to see that even though these are simple, that the process is the same no matter how far we go. So let's step it up a notch and do something like this. Oh, I should stop the recording. Sorry.